Dear third grade students, welcome to our fifth recorded lecture for the course entitled Computer Applications in Management and Economics. I continue lecturing you in the economic part of the course. Bear in mind that the recorded lecture is to be used in conjunction with your textbook. In the previous two lectures, we studied Chapter 4, in which we introduced graphs that are commonly used to present information about different datasets. In other words, we introduced line graphs, histograms, and bar charts to summarize the main features of time series datasets, cross-sectional datasets, and panel datasets. Graphs provide an immediate visual impact that is useful for livening up an essay or a report, though in many cases it's important to be numerically precise. Therefore, in Chapter 5 we discuss briefly a few summary statistics for summarizing the main features of quantitative data and how to use EVUs to compute such summary statistics. To numerically summarize a dataset, we use central tendency measurements that are averages of the dataset. Averages are important, but they tell only part of the story, so we need other measurements for the variability of datasets, such as the standard deviation. Variability measurements tell us the amount by which data points are scattered in a distribution. In previous lectures, when studying histograms, we recognized that data points are likely to spread around their mean in a symmetrical or asymmetrical pattern. Thus, we need a statistical measure to inform us whether a dataset is symmetrical or not. That is the skewness. Moreover, another important feature of the data points is whether they have thinner or fatter tails compared to the normal distribution, as we mentioned earlier in previous lectures. That measure is the kurtosis. Fortunately, EVUs provides these summary statistics. Thus, the current chapter instructs you how to compute them using EVUs. You already know all statistical measures discussed in Chapter 5 from other courses, such as the course of Descriptive Statistics that you studied in your first grade. However, let's quickly resume these measures. Central tendency measurements of data enable us to obtain one single value, that is the average. The average describes the location of data. In other words, these measures inform us about the value around which the data points tend to cluster. These averages are the mode, the median, and the mean. The mode is the value that occurs most frequently. It is the only sensible measure of central tendency for nominal data, since it could be reasonably interpreted. For example, you may read in a newspaper that the most frequently sold motor cars in the last 2 years were silver. If the data under consideration is numerical, it is possible to compute the middle or median value. The median indicates the middle value when all data points are ordered from least to most. If a variable has an even number of data points, the median occurs halfway between the two middle data points. An important advantage of the median is not being affected by extreme values of the data. The third measure of central tendency of data points is the mean. The mean value incorporates all observations in a sample. To compute the arithmetic mean, all data values are added and then divided by the number of observations. Calculating the mean is meaningful when using numerical data. The arithmetic mean, unlike the median and the mode, is sensitive to the presence of extreme values or outliers. It is highly recommended to report the values of the mean and the median if the data distribution is asymmetric. Differences between the figures of the median and the mean indicate the existence of a skewed distribution. Kindly refer to Figure 5.1 and Table 5.1 in your textbook for more illustration. Describing the dispersion of the data is important as explaining its central tendency. The most commonly used measures of describing data dispersion include the range and the variance, or the standard deviation. These dispersion measures are appropriate only for quantitative data. Measures of dispersion are descriptions of the amount by which values are scattered in a distribution. Measuring data variation reveals the reliability of an average through indicating to what extent an average is representative of the entire sample. Moreover, dispersion measures enable us to compare two or more data distributions in terms of their variation. The range is simply calculated as the difference between the maximum and the minimum values of the dataset. However, this statistic is infrequently employed in applied research since it is highly influenced by the presence of the extreme values. The standard deviation describes the extent to which values differ from their mean. The standard deviation is the square root of variance. In general, it could be viewed as the square root of the mean of all square deviations from the mean of the data points. Unlike the variance, the standard deviation describes data variation in original units of measurement such as dollars, kilograms, and so on. Now assume that you want to compare the relative variability of data between distributions of different magnitudes or even different units of measurements. For example, you may desire to compare the variability between two datasets where one set is measured in hundreds of tons and the other is measured in billions of tons. The question is, what is the statistical measure that is meaningful in such a comparison? For such a comparison, the coefficient of variation is to be computed. It is a unit free. It is calculated by dividing the standard deviation of each dataset by its mean and then multiplying the outcome by 100. The distribution that has the largest coefficient of variation is said to have the largest relative variability of data. As mentioned earlier, skewness measures the lack of symmetry in a distribution. In other words, skewness measures the extent to which a distribution of a dataset is concentrated at one end or the other of a distribution. If the value of skewness is 0, the distribution is said to be symmetric, and there are no extreme values in a particular direction. Thus, the mean equals the median and the mode. A distribution is said to be symmetric if a vertical line drawn from the center of the curve to the horizontal axis splits the area under the curve into equal segments. If the coefficient of the skewness is positive, the distribution is said to be skewed to the right. Thus, The data points are concentrated more towards the left with few observations in the right-hand side of the distribution. In such a case, the distribution has longer tail towards the higher figures. Positive skewness arises when the mean increases by some unusual high figures, thus making the mean greater than both the median and the mode, whereas the median is larger than the mode. Finally, if the coefficient of the skewness has a negative value, the distribution is said to be skewed to the left, indicating that the data points are concentrated more towards the right with few observations in the left side of the distribution. In such a case, the distribution has longer tail toward the lower values. Negative skewness occurs when the mean decreases by some extremely low figures, thus making the mean lower than the median and the mode, whereas the mode is greater than the median. As mentioned in the previous chapter and in the previous lectures, kurtosis measures the degree of tail heaviness and or weakness of a data distribution. Two curves with the same central location and dispersion are likely to display different degrees of kurtosis. The importance of knowing the value of the kurtosis has been already discussed in chapter 4 and in the previous two lectures. The normal distribution has a value of kurtosis that is equal to 3. A distribution that has a value of kurtosis equal to 3 is said to be mesocortic. If a data distribution has a kurtosis value that exceeds 3, it is said to be leptokurtic. In other words, it is more peaked with longer tails relative to the normal distribution. In contrast, if a data distribution has a kurtosis figure that is less than 3, the distribution is said to be platykurtic. In other words, it is flatter with thinner tails compared to the normal distribution. Computing of data summary statistics is an important task when dealing with numerical data. Fortunately, EViews enables us to compute summary statistics for one variable or a group of variables using menus. Summary statistics provided by EViews include mean, median, standard deviation, skewness, and kurtosis. Moreover, the minimum and the maximum values of data points are provided. Furthermore, EViews computes the statistic of Jar-Kipira and its probability. This statistic is computed according to the formula shown below. For a normally distributed variable, as you already know, Skewness coefficient equals 0 and Kurtosis coefficient equals 3. Thus, for a variable that follows a normal distribution, the Jar-Kipira statistic is 0. Therefore, if the value of the Jar-Kipira statistic for a certain variable is close to 0, then we could say that this variable follows a normal distribution. It is worth mentioning that if the probability attached to the Jar-Kipira statistic is lower than, say, 5%, we could say that we are 95% sure that the distribution of the variable under consideration doesn't follow a normal distribution. As mentioned earlier, employing if-use menus help computing the summary statistics for one variable or for a group of variables. The question is how to do so. In other words, which menu is to be used to obtain summary statistics. The view menu from the series or the group title bar is used to obtain summary statistics. Let's start showing how to obtain these statistics for a single variable. These steps are described in details in your textbook using screenshots 5.1, 5.2, and 5.3. Double-click on any series of interest to open it. From the title bar of the series, click on the View button. A drop-down menu with a number of options appears, as depicted in the screenshot 5.1 in your textbook, and as shown in the current slide. Kindly note that this drop-down menu has the options that enable us to graph a single variable, as we discussed in the previous lecture. It is highlighted in yellow. This option is named Graph. Moreover, the option used to obtain summary statistics has also been highlighted using the same color. This option is Descriptive Statistics and Tests. There is an arrow next to this option indicating that if you click on it, another drop-down menu appears. Let's click on it. By doing so, the drop-down menu shown in the right-hand side of the current slide appears. The first three options are of importance to us in the current lecture. The first option enables us to obtain summary statistics along with a histogram showing the distribution of the data points. The second option provides the summary statistics of the variable under consideration in a table. Finally, the last option enables a researcher to obtain the summary statistics for different units included in the sample. Thus, it's relevant for cross-sectional datasets and panel datasets. Now, let's follow the aforementioned steps to obtain the summary statistics along with a histogram for the variable named GDPPC. As you know from previous lectures, this variable represented the cross-sectional data on real GDP per capita in the year 1992 for 90 countries. Thus, we obtained the screenshot 5.2 in your textbook, which is shown here as well. Note that the top of the statistics section in this screenshot shows the name of the series, the name of the variable, the sample, and the sample size. In the middle of this statistics section, if-use summarizes the main statistics for the series. These statistics include the mean, the median, skewness, and so on. The bottom of this section shows the Jar-Kupira statistics and its associated probability. The summary statistics in the attached screenshot shed light on the cross-country variation in GDP per capita. Let me explain. Kindly look at the minimum and the maximum values of this variable. The minimum value for GDP per capita is $408, whereas the maximum per capita GDP exceeds $17,000. Hence, the large distance between the sample maximum and its minimum reveals how scattered the distribution is. An important part of data description is the ability to compare basic statistics across different units, such as countries, students, and so on. In Chapter 4 and in the previous lecture, we compared the hourly wage in 3 developed countries, namely the United States of America, Canada, and the United Kingdom in 2 years. Now, an important question is how to obtain summary statistics with the hourly wage for each country and for the whole sample. It is very easy to get these statistics by following the aforementioned steps and selecting the option stats by classification. Let me repeat these steps again to remind you. First, double-click on the hourly wage series to open it. Then select the View menu from the series title bar to bring the drop-down menu shown in the screenshot 5.1. Then select Descriptive Statistics and Tests to bring up the sub-drop-down menu in which there are 3 options related to computing summary statistics. Then click the third option, that is Stats by Classification, to bring up Statistics by Classification dialog box. This dialog box is displayed by the screenshot 5.7 in your textbook, and it is shown in the right-hand side of the current slide. As you see, it has 6 sections. Under the Statistics section, take the statistics you wish to compute. In other words, put the correction mark next to each statistic you want to compute. For the current example, I already checked the buttons of mean, median, maximum, minimum, standard deviation, skewness, kurtosis, and the number of observations. Under the top middle section, that is entitled Series or Group for Classify, type the word country, which I highlighted using yellow color. Under the top of the right-hand side section that is entitled Output Layout section, take the 3 boxes under the table display. Finally, leave the remaining sections to use default. Then hit the OK button. Once you do so, the screenshot 5.8 appears. We will discuss this screenshot in the next slide. Screenshot 5.8 displayed in the current slide provides the summary statistics of the hourly wage variable for each individual country and for the whole sample. Note that the last column gives the number of observations for each country. It is clear that each country has the same number of observations, that is 20. Hence, the dataset under consideration is a balanced panel with a total number of observations equals 60. The computed Kurtosis Coefficient is displayed in the 8th column before the last one. According to the Kurtosis value that is considerably less than 3, the distribution of the hourly wage for each individual country and for the whole dataset seems to be plateautic. Regarding the skewness measure, it has a negative value for Canada and the USA, but a positive value in the case of the British data. However, the value of the skewness is very close to 0 for both the USA and the UK. Bearing this in mind and to be cautious when comparing the average of hourly wage in the three countries, we employ the median to measure the central tendency of the data. Thus, we could say that on average, Americans and Canadians received the same hourly wage, but the British workers received the lower wage per hour, that was around $75. Taking into consideration that the hourly wage in the three countries is measured in terms of the US dollar, real US dollars, we can use the standard deviation to compare the variability of the data. Hence, we could say that the UK data displayed the largest variation with a standard deviation of $27.66. This is followed by the USA and then Canada, whose standard deviations are shown here in the current slide. Details of obtaining the summary statistics for a group of series are shown in the screenshot 5.4 and 5.5 in your textbook. As for the single series case, we double-click on the group of interest to open it, then we click on the View button from the group title bar. A drop-down menu appears as depicted in the screenshot on the left-hand side of the current slide. Pay attention that this drop-down menu has the option named Graph, which allows us to graph a group of variables as we illustrated in the previous lecture. This option is highlighted in yellow. Furthermore, the option used to obtain summary statistics has also been highlighted using the same color. This option is Descriptive Stats. Note that, and as mentioned earlier, there is an arrow next to this option indicating that if we click on it, another drop-down menu appears. Hence, by clicking on it, the drop-down menu shown in the right-hand side of the current slide appears. This sub-drop-down menu has two options. The first option is Common Sample, and the second option is Individual Sample. For the example under consideration, there is no difference since we have no missing values for any of the four series. If we select the first option, that is Common Sample, the summary statistics table depicted in the screenshot 5.5 in your textbook appears. Let's briefly discuss these summary statistics in the next slide. Screenshot 5.5 that is displayed in the current slide provides the summary statistics computed for the US dataset we previously employed. Let's compare the median of each variable with its own mean. Why do we perform such a comparison? Well, the answer is very easy. Recall that we have mentioned earlier in the current presentation that in a positively skewed distribution, the mean of a certain variable is greater than its own median. Thus, given that the mean for each series is larger than its own median, we could say that all series have asymmetric distributions that are skewed to the right. Thus, the median is a better measure for the central tendency of data points than the mean. Now, let's look at the coefficient of skewness for employed variables. it has a positive value for all variables, confirming our conclusion when comparing the median and the mean. Positive skewness implies that the mass of data points are concentrated to the left of the data distribution and few observations lie in the right tail. With regard to the Kurtosis coefficient, it is less than 3 for the series of GDP, M1 and BR. Thus, these three series are platy-quartet, implying that their distributions have shorter tails compared with the normal distribution. In contrast, the interest rate series that has the sample RS is leptokurtosis, given that it has a kurtosis value which is greater than 3. Based upon the values of kurtosis and skewness, all series are not normally distributed. This conclusion has been also confirmed by the Jar-Kibira statistic and its associated probability. Note that the probability or the p-value, that is the exact level of significance, is 0, which is lower than all conventional levels of significance that are 1%, 5%, and 10%. Hence, we are sure that the Jar-Kibira statistic is significantly different from 0 for all variables, indicating that all of them do not follow a normal distribution. Now, let me ask you a question. Could we use the standard deviation for the employed variables to compare their relative variability? Let's answer this question in the next slide. We have raised a question of whether to use the standard deviation to compare the relative variation of series under consideration. Given that these series are measured in different units, we couldn't use the standard deviation to compare their relative variability. I mean that the interest rate is measured in percentage, where the real GDP and M1 are both measured in real US dollars. Finally, and as you already know from the course of macroeconomics, the price level is an index number. Hence, to compare their relative variability, we use the coefficient of variation as mentioned earlier in the current presentation. Recall that the coefficient of variation is a unit free and it is computed by dividing the standard deviation of each series by its mean and then multiplying the outcome by 100. The distribution that has the largest value is said to have the greatest relative variability of data. But EVUs doesn't provide the coefficient of variation directly. Therefore, we could convert the mathematical formula introduced by equation 5.3 to compute the coefficient of variation for each variable into a code that is understood by EVUs. Screenshot 5.6 in your textbook is shown in the current slide in the left-hand side. This screenshot provides the codes used to create these coefficients of variation. The first line gives the required code to compute CV1, that is the coefficient of variation for the GDP series. The second line provides the code required to compute CV2, which is the coefficient of variation for the M1 series, whereas the third and the last lines display codes required to calculate CV3 and CV4, which are the coefficients of variation for BR and RS respectively. After typing each code in the command window, hit the Enter key. The screenshot shown in the right-hand side of the current slide depicted the coefficients of variation for this series. It is clear that GDP data distribution exhibits the largest relative variability, given that it has the largest coefficient of variation. On the other hand, RS data distribution shows the smallest relative variability since it has the lowest coefficient of variation. The current presentation discussed the main points of Chapter 5. The focus of this chapter is to describe quantitative data using statistics. Measures used to summarize the quantitative data are central tendency measurements, variability measurements, skewness as a measure of asymmetry of data distributions, and finally kurtosis as a measure of tail heaviness of data distributions. Furthermore, the chapter gives instructions to compute summary statistics for a single variable and for a group of series using different data structures. We concluded that if a distribution of data points is asymmetric, then the median is a better measure of central tendency. Moreover, the standard deviation is used to compute the relative variation of data distributions if different series are measured in the same units. If not, the coefficient of variation is employed for such a comparison. Data distributions that have kurtosis values that exceed 3 are said to be leptokurtic, whereas they are said to be plagiocurtic if these values are lower than 3. The view menu from the series title bar is used to obtain summary statistics for a single variable. Similarly, the view menu of the group title bar is employed to obtain summary statistics for a group of variables. Finally, we use the command window to execute the codes required to compute the coefficient of variation to compare relative variation of variables measured in different units. This is the end of our lecture. Thank you.